Okay, so this is the last video for class number 11 in fluid mechanics, and this is video 5, and we're going to do another example. I forgot to include this one right here from Sengel. It was a pretty one, pretty pictures showing them capturing some hydraulic power from a reservoir and being able to generate electricity with it. But anyway, here's the problem that we're going to work on, where we're going to incorporate some additional stuff, right? So let's see. So we have a pump right here. Is going to be used to move water from a lake into this large pressurized storage tank. And it's going to be 1,000 gallons in 10 minutes. Will a pump that adds 3 horsepower of water work for this purpose, right? So we're doing a sort of a pump sizing type of exercise here. And we're going to support your answer with appropriate calculations. And then we want to repeat the problem if the tank is now, instead of 2 atmospheres, pressurized to 3, and see if it'll work. I might actually also maybe incorporate some losses as part of this, just as a demonstration. So, okay, here's our situation, and we're moving from this body of water up to this. So a good starting spot is on the surface. It helps out. We could do on the inside of the pipe, but then we'd have to worry about the velocity. So going to the surface right here, we could maybe draw a single streamline, hypothetically, that comes all the way up here and comes back up to there, where once again, that tank could be so large that the velocity, we could assume, is going to be 0 right up there, right? So the width of this tank could be so large. And it's moving up 20 feet. And they didn't give us the dimensions of the pipe, so that would have been a clue that we could not have done anything with the velocity. So the volumetric flow rate here is going to be that 1,000 gallons divided by 10 minutes, or you could do this in your head, 100 gallons per minute, or 7.48. Oh no, we're going to need to divide. Sorry, my bad. Divide by 7.48 gallons per cubic foot, divide by 60 seconds per minute, and what we're going to end up with is 0.2228 cubic feet per second. So that's the volumetric flow rate. So now let's go Bernoulli between 1 and 2. And the way I've been writing out this go-to equation for Bernoulli 2 is to say the pressure up here divided by the specific weight. We have the velocity at 2 divided by squared and divided by 2 and divided by g. You're going to have the z2, and that's going to be equal to p1 divided by gamma plus v1 squared divided by 2g and z1. And now we're going to add pump head, and we're going to subtract out pump losses. So up here, we know what that's going to be. It's going to be 2 atmospheres. We're good with there. We said already that we're going to go up to have a large enough tank so the velocity here doesn't matter. We're going to come up 20 feet. So like right here is what we're going to consider the datum. So we can come over here and say this is going to be 0 because it's at the datum. P1 starts right here, so we're going to say that it's atmospheric. And V1, we're going to say that's going to be on the surface of this, and it's going to be small. We might even, for the time being, say that the head losses are negligible. So what we're going to end up with is at P2, we're going to have 2 times 14.7. So it's going to be, what, 29.4? Is that right? 29.4 psi G. And we want to turn that into pounds per square foot and divide out. This is fresh water, so 62.4. And now we're going to have the amount of head that we have to have into this tank. We're going to add the 20 feet that has to go upwards. And then that's going to end up being our pump head. So that pump head that we have to add is 87.85 feet. And so the pump, what's required in order to do this, it's going to be the useful, that's what they had right here, is going to be HP times gamma times the volumetric flow rate. So 87.85 times 62.4 times 0.2228 divided by 550, and we're left with 2.221 horsepower. Therefore, we're okay, because we were asked as part of the question, will a 3 horsepower pump do it? And then they said to repeat the problem again if we have 3 atmospheres rather than 2 atmospheres. So all we have to do, I won't try to do any shortcuts here. We could just put in 3 atmospheres. Still pumping up 20 feet. And so this is going to be HP, so I'll make this equal to 121.8 feet. So the pump useful power that it has to do work on is 121.8, 62.4, 0.2228 divided by 550. And we're left with 3.078 horsepower. Therefore, nope. Now, in some of the homework problems, or the homework problem that I have put in here for you, I incorporated some head loss, and none of these problems have head loss in there. So jumping ahead to stuff that we will learn later in the semester, head loss is often related to velocity, in the pipe. So like if you look on the inside of the pipe, might be like kind of rough right here. So because of that, there's going to be like losses along the inside of the pipe. You're also going through fittings. As you go through an elbow, you get little losses that are taking place as you go through. As you go through valves, right? Here's a little diagram of a valve. Well, some of the valves have a different passage that it has to go through. There's the globe valves, and they cause losses. Even the inlet and the outlet, even the act of water coming into this inlet or coming out of this outlet inside the thing, causes some losses. And they're all really related to the velocity of the water. So one of the head losses that you might see a lot of times, you might have some kind of thing in front of the velocity squared divided by V2. So you remember we had this dynamic. This is actually what's happening at whatever location you happen to be picking the point. So we could have picked a point like that was inside the pipe right there. We would have had to include, or like right into there. If we had picked these points instead as 1 to 2, we would have needed to include 1 from right there and 2 from right here. It was only the fact that we were able to have a strategy to get rid of them by picking them out here to the surface that we didn't have that. But we still have that kind of concept of the dynamic. We have some kind of factor that we put into there. One for the piping one, not to jump the gun too much, we have something, a little script F, and we'll have the length of the pipe divided by the diameter of the pipe, and that is one form of the thing, right? Or we might just be given this. So in the problems, like one problem I saw recently used 61, right? So this is dependent on what system of units that you're working on. It's not non-dimensional, but it was sort of like an amplifying factor to the dynamics right here. So it's a V squared over 2G. So in order to do this, maybe to make as a gross estimate, right? So this might be some estimate that we were given, right? So this is not a number that you can depend on. It's only specific to maybe somebody already did some of this for you. These are considered the major losses. These are considered the minor losses, and sometimes they might add some stuff inside here, but they're all getting multiplied by here. So I gave you some factor times there, and sometimes you might even like combine these together and multiply by it in there. But anyway, let's say for instance, we have 3-inch ID pipe for our scenario. So if we want to find the velocity, we take the volumetric flow rate divided by the area. So we were given a flow rate of 0.228 cubic feet per second. So we could go pi over 4 and 3 divided by 12, get it into feet squared, and go for the Hewlett-Packard calculator here and say 0.228, and then let's say we go pi divided 4 times 3 12s divided square it divide, and we have that's 4.6448 feet per second. So in this instance, 61 and our 4.686. I don't know what the hell I'm doing here. I'm tired. I'm going to make another whole set of videos here in a second. That's not really good. Doesn't sound like it's ever going to be a very good idea. But anyway, I'm going to do it anyway. Divided by 2 and 32.2. And so the head losses, let's see, I'll square this. Boom, squared. And 61 times 2 divided, 32.2 divided. And you get losses of 20.44 feet of head losses, right? Let's go back to this guy up here, and we'll say, well, what if we had those head losses right here? What if they weren't negligible? So what we would do here is they would show themselves as negative right here. I'm going to write on a separate piece of paper. Let me see. Look at a separate piece of paper. If I could find my kingdom for a pad of paper. So, continuing on, we would say that we have from up above, we had HP is now going to be equal to the 87.85 plus our 20.44. So 87.85, add them in there. So now we have 108.3 feet is what the pump head has to be, because now it has to not only hit it head, but it had these losses as well that had to be put onto the other side. So now the new work or power, rate of work, that has to be done then, the useful one is going to be 108.3 times our 62.4 times the flow rate divided by 550, and we end up with 2.737 horsepower. So we would still be okay with that 3 horsepower, but we already went over it when it came to this guy right here, right? So when we were just looking at what would happen if we had to pump up against there. So we have to, this is more of a demonstration of a typical problem. If you will take a look at our homework, I was told by at least one student today that they were a little intimidated by this. So let's take a quick peek at it if you happen to be watching this video. This would be helpful. They said this was intimidating. You know what I thought was intimidating? It's probably this duck. This duck was very intimidating. Okay, so here's what I did is I guess I did kind of make this a little bit, but it's very similar to what I had just mentioned before. Is I gave you what this friction constant was, and you can find what the total length of the pipe is going to be. for each of the things, right? So what did I say? I said we have a 4-inch diameter pipe on the inlet, and we have a, where's the outlet diameter? Oh, we have 3.5 inch. And this is very common that the suction will be larger than the output. But you could estimate the amount of pipe by just taking y1 plus y2 plus x1. That's the length of the pipe that's going to be coming in on the inlet, and it's got a diameter of 4.5 inches, right? And then we have this coefficient of friction, or this friction factor, so friction constant. And so find the velocity that's inside this right here, because we have the flow rate, 1,000 gallons per minute. And you can find out what the head loss is here. And you're going to have an additional head loss that's over here. And those head losses, even though they're one's on the inlet, one's on the outlet, they're just going to be the total head loss that you would have as part of this. And then, so you also do it for the outlet side. You would find, we're going to ignore the fact that this thing has a height to it and just take y3 plus x2 plus y5 plus y4, and that's going to be length of all of this stuff to get to the outlet of there. And those are also going to be head losses, and we're ignoring the minor losses. So that's going to be the HL, and the rest of it is going from the start here at 1 and then go to 2 up here by the duct, and you'll be able to find what the HP is. And then with that HP and the volumetric flow rate, you'll be able to find what the power is necessary for the pump. And then you need to divide by the pump efficiency and then divide by the motor efficiency, and you'll be able to get what the electrical power is in horsepower. And then you need to look up what the conversion from horsepower to kilowatts is. You could probably do this problem, I'd say, in 10 minutes. But I just narrated for you, described it. Maybe it'd take you 20 minutes. I don't know. But from what I just described, I think you can work through the same thing. And then for the turbine, the same kind of idea, but working backwards. But here we do need to have, remember, we do need to have what the velocities are going to be in there. And we're also going to need what the pressures. But we can get what the amount of head that can be extracted by this turbine. And then we can, now we're going to apply the efficiencies, but we're going to be multiplying by them, because we're going to take a hit when we go from this hydraulic power into the turbine output to get to the shaft. And then we're going to take a hit when we go from the shaft to go to the generator. I hope that helped a little bit. I don't know how many people are going to watch this video to the end, so, but I just want you to admire the fact I put a little fish in here and I put a little crab. It's a little crab. It's fun. I made all these in PowerPoint. I made all those little things just for you. Anyway, hope that isn't too intimidating. I don't want this to be torturous, but I want you to have an experience where you get some stuff out of this. So that is it for this video. Hopefully you'll like it.